This is a follow-up to a video I published back in November 2018 featuring our 360-degree robot radar. There's a link in the description. There was at that time several examples of sonar ranging projects for hobby robots, but none of them seemed to be capable of 360 degrees coverage. I put together a working example and posted a video on YouTube to see if there was any interest. There didn't seem to be very much interest at all in my version. About 3,800 views in over a year, a few subscribers, a few comments. A couple of people asking me to rewrite my code in processing, then show them how I did it. Bless them. Unfortunately, we often don't have the time to guide the newbies through the development process. So the 360 radar project has more or less been on the back burner for a year or so, mainly due to a lack of interest. Skip forward to April 2020. That means a few weeks into the coronavirus outbreak, or what we are calling the zombie apocalypse. Most of us are now locked in with nothing to do except dig out our ham radios, Raspberry Pis and Arduinos and do the stuff we used to do when we had time on our hands. First of all, we can all learn a lot about designing, engineering and 3D printing in the course of a year. So obviously the design has changed from the original. Let's take a closer look. This is what the current version looks like. This is what it looks like when it's dead. We won't dwell on that. Let's concentrate for now on the internal components, which look like this. We'll take a look at each of these individually, starting with one of the two gears. This one we are calling the input gear. This is 3D printed using PLA, 10 teeth, about 27mm overall diameter. One end has a hole with two flat sides to accept the stepper motor shaft. The bore is 5mm diameter. The flat walls are 4mm apart. The flat part on the stepper motor shaft is 6mm in length, so the flattened hole on this side is 6mm deep. The other side has a 5mm diameter, 7mm deep hole in the centre, which is designed to accept this component. Mild steel, 15mm long. Each end is 7mm long with a 5mm diameter. The centrepiece is 7mm diameter, about 1mm wide. You could probably spend 15 minutes or so spinning one of these up on a lathe, or you could buy 1,000 of them for about £14, dollars, euros, whatever. These are in fact the small pegs which are used to support shelves in those flat-pack piles of junk we all love to buy. Thanks, IKEA. And so these components go together like this. They are attached to the stepper motor, and when the stepper motor is screwed into the housing, the input shaft assembly is correctly aligned and held in place. Let's now take a look at the output shaft components and how they fit together. This is the second of our custom components, the output gear. Very similar to the input gear, 3D printed using PLA, 10 teeth, 27mm overall diameter. The only real difference is the centre bore. It does not have any flats because it isn't fitted to a stepper motor shaft, so it has a 6mm bore all the way through. Remember, the input gear bore was 5mm. The output gear bore is 6mm because it has to be coupled with our next custom component. The output shaft is made on our mini lathe out of some 6mm stainless steel bar which we had in stock. Looking at the dimensions, each end is reduced to 5mm to accept the bearings we have in stock. The 6mm diameter section of this part allows for a good press fit into the output gear. The output shaft is also hollowed through the entire length with a 3.5mm bore, leaving a 0.75mm wall thickness along the 5mm diameter sections. A quick look at the bearings we're using. 16mm outer diameter, 5mm inner diameter, 5mm thick, and this project uses two of them. The first one goes here to receive the output shaft. The second bearing goes into the back plate to support what will be the underside of the output shaft. Although it was mentioned in the previous video, I will briefly touch upon the 28BYJ48 stepper motor. Only briefly, because it would appear that there are different types, manufacturers, voltages, gear ratios, etc, etc. We have noticed inconsistencies in the past. We would need more experimentation to expand on that. But for this example we are using a 12 volt version which appears to have 2048 steps per full revolution, but we will cover this in more detail later in the software video. Then on to what is possibly the most important part of this project, the slip ring. This is the device that allows cables to pass through from the base to the rotating top part without becoming twisted. Since we're using this rotator as a base for our robot radar, we have printed this mast to hold the HC-SR04 ultrasonic rangefinder. That just about covers the hardware for this project. In the next video we will look at the software we use to make it live. Please like, subscribe and tell your friends, and as always, thanks for watching.